So when you look at uniform acceleration, we derive a bunch of formulas for this, and we have done straight line motion. You have done this in the 9th standard. You have done it. We have done this a couple of classes also ago. So you have all these various formulas. V equals u plus at, s is ut plus half at square, right? V square minus u square is 2as. We have done all of these. But there is no formal way of doing this which is valid when you have non-uniform acceleration. This is something that we did specifically for uniform acceleration. Suppose the acceleration was not uniform. Suppose it was changing. Okay. Suppose you had velocity which was varying, but not like this. It was varying in a weird way. Then how do I find what is the displacement? How do I find out what is the acceleration? So all these are much more tricky questions than just this. Because they are tricky, in 9th standard, you restricted ourselves with just uniform acceleration. What is easier than uniform acceleration? Uniform motion. Okay. Well, if you had uniform motion, what happens? Uniform velocity is uniform motion. Then you can just say S is equal to Vt. Nothing changes. Suppose you go one step before this. That means there is no change in position. So what is the object doing? It just remains at rest. So there is nothing to do in that kind of a question. So this is slightly easier than that, but that's also relatively easy. Suppose I want to study a situation where the velocity of the object is continuously changing. Okay? It is still going in a straight line. But what is happening is, let's say it started here. Then after a little while it went there, then it went very fast, and then it slowed down. Okay, so its speed is changing. I can't even say reducing because it was increasing and then decreasing. We sometimes will draw it using a graph. We will say, let us try to draw a velocity time graph. The velocity was positive because it's going in that direction. Let's call that positive direction. We still have to define something as positive. But the velocity was increasing because let's say the first 1 second it traveled this much, second 1 second it traveled that much because its velocity is increased. But if I try to take this distance and divide by 1 second, I will only get average velocity. I don't know what the velocity is here. I don't know what the velocity is there because the velocity is changing throughout. So maybe the velocity was doing this. At this point the velocity was very small and then it kept increasing. So when it was here, the velocity was much larger. And then after that the velocity started to drop. It has not yet come negative. It's still positive, except that it is a smaller positive, so it's going down. It may happen that after some time it slows down and it stops. If that is the place where it stops, how will that look on a graph? Velocity will become 0. And after that, let us say it starts to come back. Velocity becomes negative. Maybe it does this. Okay? Now think about a graph like this. This is telling you how the velocity varies as a function of time. We say velocity as a function of time. So we say v of t. Sometimes people will write v at time t like that. Sometimes they'll just say v and not say anything extra. But that v is not velocity at a particular time. It is not velocity here or there or there. It is this whole graph. So we are talking about this will probably be like a formula in t. Okay, we say function of time. I want to find this when I know how the particle is moving. Okay, I want to find out what is the object's velocity. I am telling you the particle is moving. Let us say we are able to observe the particle. Let's say the particle is me. Let's say right now I am walking and then I am doing this, then I am stopping, then I am again walking. So if you see, I was doing this, then slower, and then maybe this way, and then that. I am doing different things. If you knew exactly what I was doing, will you be able to find the velocity at a particular time? Is the logic of this first clear? Okay, that's what we want to find. And then similarly, we will want to find out what is the acceleration at a particular time. The tool, the mathematical tool to do all this is called calculus. So we'll learn a little bit of this mathematics and then we can apply it to all sorts of situations. So very simple. If an object is moving, let us say its position was this, and after 3 seconds, its position was that. What is its average velocity? I'll say this was x for 3 seconds. Or even better than x will be to say s for 3 seconds. This is x at, let us say, 1, t equals 1. That is x at t equals 4. I'm going to call that x4. What is this? Displacement for 3 seconds is x4 minus x1. Does that make sense? What is displacement? Change in position. So you move from this point to this point. How much did you have as change in position? x4 minus x1. What is that called? Displacement. Why am I calling it S3 instead of just calling it S? It was displacement for 3 seconds. What is the average velocity for 3 seconds? I'll put a bar to say average velocity. What is the average velocity for 3 seconds? Displacement for 3 seconds by 3. Why by 3? Because it was 3 seconds. But is this the velocity of the object here, there, etc.? No. I am interested in the velocity at 1. It is not average velocity, I didn't put a bar. I am interested in finding the velocity at time 1 second. But what I have got now is average velocity for 3 seconds. But suppose I say, wait, let's not do 3 seconds, let us do 1 second. In 1 second, will you have the same displacement like before? No. So what will you have instead? You will have S1. This will be x1, and what will this be? x2, because 1 second later will be x2. So x2 minus x1 is displacement over 1 second. How much time did it take to go from here to there? 1 second. So I can write average velocity for 1 second, average velocity for 1 second is equal to s1 by 1. Agreed? If you wanted to say the velocity at this time, we can approximately say is either v3 bar or v1 bar. Which would you prefer? Which is better estimate? It is not, both are not exact. Which is a better estimate of the velocity of the object at time 1 second? Why v1 bar? Why can't this be better? Everybody feels this is better? Why? Why do you feel this is better? Because it's telling me what I'm doing now. Whereas this is telling me what I'm doing over 3 seconds. In fact, if I took 7 seconds, that will give me an average over 7 seconds. It's not telling me what I was doing in that time, no? Correct? If I was going on a bike, if I look at my speedometer now, it tells me what's my velocity right now. But if you say, wait for 5 seconds, 10 seconds, maybe 5 minutes, I'll go and stop at this signal. If I stop at the signal, then you're counting all that and you're saying, oh, that time your speed was this average. But this is not true, because you have been now doing something else. I want to know what happens at that instant. What is better than even this? Come up with a better answer than this. So if I take 0.5 seconds, I will get V average 0.5 is what? S 0.5 by 0.5. This is better than that. Why is it better? Because you have taken a very small interval where you are looking at the velocity, average velocity. Suppose I make this even smaller, make it 0.1. Will that be even better than 0.5? So if I keep continuing like this, there comes a time where I am doing V 0.00000001, like something like that. But what will that be? The displacement for 0.0000 corresponding number of zeros, 1, by what time interval? 0.0001. Is this the better one than all the others before that? Yes. And as I keep doing it, it is getting so much better that we can almost say that this fellow is getting towards the exact velocity at t equals 1. I just picked t equals 1 here. Okay. That is time instant t equals 1. This is t equals 2. That is t equals 4. I could have picked this as t equals 2, if whatever I want. It doesn't matter. But I want you to first understand that at the principal level, do you get this idea? What is instantaneous velocity at a time? Nobody can find instantaneous velocity because you can't say there was no time. If you had no time, you would not have traveled any distance. If you did not travel any distance, what do you mean by velocity? So what is the meaning of instantaneous velocity? Allow for a little bit of time. How much is little bit? 2 seconds? No, that's too much. Okay, 0.2 seconds? Okay, better. What is even better than that? 0.0002 seconds? 0.0000001 second? That is better. Okay, so give me a really small time, find the average velocity for that small time. In that small time, there would have been a small displacement. I know this time is really small, but the displacement is also really small. Correct? So if you took this ratio, that will give me the average velocity for that small interval. That interval is so close to that instant that we assume that the object did not get enough time to change its velocity. So its velocity would have been almost constant. Is the basic logic of this clear? Okay. Why is this so important? Because we are going to use this a lot. We are going to use this a lot. I will leave this thing aside for a second. I want to plot and show you a graphical way of thinking about this. We are not going to use any of these right now, so I will erase that as well. So if I look at x as a function of time, instead of marking it here and showing what is happening, we can say at every instant this object is at different positions. So let us take an example where x starts here and goes like that. And I am interested in knowing, hey, tell me what is the velocity at this point. Let us say this was t equals 1. Exact same thing that we did here is what we are going to do there. If this is t equals 1, what is the point here called? It should be called x1. Correct? If I say this is t equals 3, let's say t equals 4, because we used 4 there, then that's a really steep one, okay. What is that? So that value is x4. So from here to there, this is the displacement in the 3 seconds. In those 3 seconds, t is equal to 1 to t is equal to 4 is 3 seconds. The object had a displacement of not like this. This is just a graph. Where is the object moving? The object is moving on this axis. Sadly, this is called x-axis. That should be called x-axis, but I'm sure you have done this in 9th also, right? xt graphs. Okay, so if the object was here, then the object is there. That means the object went from here to there. So what was its displacement? Correct? So the displacement, if I draw this line, the displacement is this. The time interval is this. We call this delta x, change in x. What is x meaning of delta x? But what does it mean? x4 minus x1. Just simply means change. So change in velocity, delta v. Change in time, delta t. So what is delta t? 4 minus 1, 3. So if I divide this by this, what do I get? Tan of this angle. It's a right angle triangle. It's called this the slope of this line. Tan theta is called the slope of this line. Just a name. Okay. So what is the slope? Well, you can understand the slope, meaning of slope, natural meaning of slope. Suppose I ask you, hey, I have these two lines, a green line and a blue line. Which one is steeper? Blue line. Which has a higher slope? Blue line. Which has a lower slope? Green line. You understand that basically, because slope, more slope means like that, more tan theta. Slope is the same as tan theta. Then why can't people just call it tan theta? They like to confuse people. So therefore, we use one extra word for tan theta, we call it slope. So this tan theta here with the x-axis is basically the slope. So this divided by that is the slope of this line. That is the average velocity for these 3 seconds. Is that the velocity here? No. But if I took instead of 3, 4, t equals 4, let's take t equals 2. Now the displacement is this much and the change in time is this much. What is this divided by this? It is tan theta, but not for that. It is tan theta for what? We call this a secant. Usually you use the word secant for what? Circles, right? In circles you talk about secant. What is a secant? Just something which cuts across 2 points. But why should that be restricted to circles? It can be you can use it for anything. This is a curve. So if you take 2 points and join it, what should it be called? What was it called in circles? Secant. What should it be called here? Secant. Why a new name? Secant is not only for circles, secant is for any curve. So if I join it, this is the secant connecting A, B. This is a secant connecting A, B dash. Now if you look at this by this, it gives you the slope of this line. Is that average velocity or is that instantaneous velocity here? What do you think? Average velocity, because over this much time it has moved this much. So displacement by time is average velocity. You know that definition, right? Average velocity is displacement by time. But it is not yet instantaneous velocity, but that's because I moved 1 second. What if I moved 0.5 seconds? Then I'll go somewhere there. Can you see that the new secant is this? And if I come closer, the new secant becomes that. And if I go closer, the new secant becomes that. And if I keep going closer, finally you will get a secant which is not touching anywhere except at A. What, do we have a name for something like that? Tangent. It's called a tangent. So these secants, this is the average velocity, this is the next average velocity, average velocity, average velocity, becomes the tangent. The slope of the tangent is the instantaneous velocity. What am I doing? I'm taking the average velocity and I'm making that point come closer. How am I making that point come closer? I'm reducing the time interval. So this time is decreasing, this height is also decreasing. It's not like the height remains the same, but you're reducing the time. You're reducing the time, height also decreases, time also decreases. So this ratio is called the instantaneous velocity at this point. Do you see that this graph and what we just did here exactly are the same? Does everybody understand that? Okay. This process we will use again and again and again. So let us think about this idea. If I took x versus t and I told you this was the x versus t graph, and I ask you, hey, tell me the instantaneous velocity here at this time. Let us say this time happens to be t equals 3.5 seconds. At that time, all you have to do is to draw the tangent and find its slope. Its slope will be the instantaneous velocity. What is slope? Move a little bit. Look at how much you go up. What you are increasing upwards divided by how much you are moving horizontally. We say rise by run. Run basically is horizontal movement, rise is vertical movement. So that is the slope of this line. So that slope is instantaneous velocity. If If you took the slope of what? Tangent. But if you just randomly took this point and that point and joined it and took this fellow's slope, what will that be called? Average velocity. Why? Because you're going to talk about this much time, and in that time you had this much displacement, so displacement by time. Of course, it includes the fact that you went up, came down, you did all that, but I can't help it. Displacement is displacement. You already know that if you went all over the place and you came back to the same place, how much is your average velocity? 0, because your displacement is 0. Average velocity, not average speed. That's easier to calculate. Average speed is harder. Okay? If somebody asks you, wait, I don't want to know the instantaneous velocity there. Hey, tell me the instantaneous velocity here. Nothing, no problem. Take the slope there. It's a negative slope. Because if I move this much, I have to go down this much. So my displacement is negative, time is still positive. Time change is still positive. For a positive time change, you have a negative slope because negative displacement. So that means the velocity here is negative. Why? Because it's coming back. When you're going in that direction, you're going up, so you'll say positive. But this guy is coming down, so it is negative. First point I want you to enter into your heads completely. The slope of the xt graph, the slope of the xt graph, that slope of the tangent of the xt graph gives us instantaneous velocity. So, in xt graph, slope of tangent is equal to v at time t, instantaneous velocity at time t. 2. Slope of secant from A to B. That is, you take 2 points and then take that curve. Let's say you take this point and join it. You get a slope for that line, right? You can pick any 2 points and draw it, join it. When you join, you get a slope. What will be the slope? Average velocity. For what period average velocity? For the period represented by this point and this point, that is from this time to this time, this period. So we'll call it TA, TB. So the slope of the secant from A to B represents or is equal to what? Velocity average. So I will use V, capital V, and put a bar on top just to say it is average velocity. Average velocity from TA to TB. For this period, the average velocity. Does that make sense? Okay. So, but the main point I want to keep in mind is that we are trying to calculate small displacements divided by small intervals of time. Is that okay? How to calculate this is what we are going to learn, and there are some simple tricks that will help us do it. But before we get there, I want you to learn one more thing, because the same trick applies to all these questions. So one more small thing, because often I also want to calculate acceleration. Okay, what is acceleration? V minus u by t. So we can write that as delta velocity by the time interval, which I will call it delta t, because t is not time interval, t is the time instant. So the change in the time instant, we have already started using that. Remember, I said t equals 1, I didn't say t equals 0, I said t equals 1, t equals 4, and time interval was 3 seconds. Unfortunately, we sometimes will use t for everything. We'll say that is also t equals 3 seconds. We'll say t equals 1 is t in time instant, t equals 4 is time instant, t equals 3 is time interval, and then we'll confuse the hell out of everyone. Okay, that's bad language and bad usage. Time instant is what we should be using, t equals 1, t equals 4, etc. Time interval we should be using delta t. The correct, because the change in the time instant. But being lazy, we'll just say t equals 3 seconds. And then I'll say, from context, don't you understand? You should use it as time interval. But that's bad habit, that's all. Okay, books will say that, schools will say that, teachers will say that, but you should hopefully ignore it and focus on what is correct. This is correct. Okay. Now the problem is, suppose like I showed you there, if I start here, I had, let us say, a velocity of some 5 meters per second. And then let us say at that point I had a velocity of 7 meters per second. And let us say this whole thing took 3 seconds. We will write V1. What does V1 mean? T equals 1. What is that fellow? T equals 4. So this will be called V4. So what is delta V? We don't have a name like S, so we'll have to use the letter delta V. So what is delta V? 7 minus 5, or V4 minus V1. But this is the change in velocity for how many seconds? 3 seconds. So sometimes I can put it like this. Delta V3. Delta V for 3 seconds. What is acceleration average? Because this is not really correct. Average acceleration is change in velocity by time. Acceleration is change in velocity by time only for one case. Which case? Uniform acceleration. But now we are not talking about uniform acceleration. We are talking about some random situation. So this is not, it's always change in velocity by time. But what is always change in velocity by change in time? Average acceleration. So what is the average acceleration for the period 1 to 4? So for the 3 second interval, what is the average acceleration?
0.6.
I know, but can we, yeah, you can write the answer as 2 by 3 meters per second square. But actually what I'm interested in is the formula or the formulation. I'm not interested in writing 2 by 3. I know the answer is 2 by 3. I'm just using numbers. What is it? It is V4 minus V1 by T4 minus T1. Or we will write delta V3 by 3. Is this the instantaneous acceleration or average acceleration? Average. If you want a better way to calculate the acceleration, what should you do? Go closer. When you go to t equals 2, you will have a time interval of 1 second. And then you will get an acceleration saying, oh, this is average acceleration for that 1 second. At this time, I am looking for 1 more second. I am giving it some time. Do I need to give it any time? It's instantaneous, no? But if you gave it no time, velocity won't change. So you have to give it some time. Otherwise, how will you calculate? But if you gave it 1 second, it's not instantaneous, it's average for 1 second. What is average for 1 second? At this point, you will get V2 minus V1. So you will get V2 minus V1 by T2 minus T1. What is V2 minus V1? Delta V for how long? 1 second. For that 1 second interval divided by 1 second. This is better than this. Clear? What is better than that? I can do 0.5. But I already know. 0.5, is there something better than 0.5? 0.01. Is that better than 0.01? So really give it a very, very small time. How small? However small you can. We write this complicated mess like this. We say, hey, I'm not going to tell you how small. I will make it smaller and smaller and smaller and smaller, so small that you cannot even figure out what to do after that. So we'll make this fellow delta t go off to 0. We'll make it so small that it's becoming 0.001, 0.00001, 0.00001. So that's becoming so small. What is it becoming? 0. It's not yet become 0 because if it became 0, I cannot divide by 0. So I won't make it 0. But if I got to 20 zeros and 1, and then somebody comes and says, hey, is that small enough? I'll say, no, I'll add 20 more zeros. So I'll make it 40 zeros. It looks like a very cumbersome thought process, but you're not actually going to do the calculation. So it's okay. So you will make this guy really small, and then we will write, this is the change in velocity by the time interval. When this time interval is very small. But when the time interval is very small, what will happen to this fellow? Really small. Okay, for example, I'll just use approximation. I cannot use it as exact. Okay, so the approximation will be, what is a good way of doing it? will be delta V. How small should I take? Just pick some number. Is this good enough? Delta V 1 by 1? That's not good enough, right? So what can we do? 0.0000. Take the same number of zeros and put it below. So this is the delta V for that much time, which is not going to be much, right? Because it wouldn't have changed much, right? But it has changed by a small amount. Divided by the time is the rate at which the velocity is changing. This is instantaneous. This is average acceleration for that interval, but the interval is so small, there is no interval. After some time you have reduced the interval so much. So what should we call it? Instantaneous acceleration. So we write this as A at time t. We don't write it as A bar. Okay, we just call it A at this point. We don't even sometimes write it as A of time t, we just say A. With this complicated mess, we call dV by dt. And we will write A is dV by dt. In the same form here, remember we should have written what? What should have written for velocity? We should have written change in x, displacement by the time. When you made time become really small, what does this mean? Take the case limit when delta t, the time interval, is becoming tiny. So what does that mean? First you do it for 3 seconds, then you do it for 1 second, then do it for 0.5, then do it for 0.001, 0.00001. Maybe at that point you can stop and say, I've got it small enough. Now if somebody doesn't like you, they can say, no, go for another 20 more decimal places. But at some point you will go that close. Have you gone to as far as you want to? Yeah, if you have, then that's it. That value that you have got, you took a it's not like delta x is for any x change, right? But when we say this, we are not saying any x. We are saying make it so small that nobody will complain. See, the problem is if I took 3 seconds, she may be happy. She's not even complaining for 3 seconds, but she may complain. I'll say, okay, let's pacify both. We will take it as 1 second. Are you happy? She says, okay. She says, I was happy even for 3 seconds. So I'll of course be happy for 1 second. So both of them are happy. So okay, shall we stop at 1 second? And suddenly that guy gets very upset. He says, no, 1 second is too large. How much do you want? Okay, he says 0.1. Okay, we'll take 0.1. So now all three of you are happy. Then suddenly this guy decides, no, I want it to be 0.000001. At some point everybody is satisfied if we take a really small number, right? So we'll take that smaller number. If somebody complains, we'll take a smaller number. But nobody can complain and say you must take 0, because then with 0 we can't do anything. But let's come to an understanding, all of us, to pick the smallest number we all agree upon. That seems a little random, but it's not. Because if all of you come and say, okay, we'll all agree on 10 seconds, I will say, no, I won't agree. Right? So, as long as somebody comes up with some number which is the smallest number that you want to kind of stop at, that's good enough. Take that. So what does this say? Pick the smallest number all of us are happy with. It cannot be 0. That's why it's not equal to 0, it is going to 0. So take such a small number, take the delta x, delta t, everybody is happy that now it won't have changed much, right? So you will get some answer to this question. That is the instantaneous velocity. But instead of writing this very messy looking big thing, limit delta t goes to 0 and all that, we want to say, hey, pick a really small change in time. So small that nobody will complain. What is that time? We'll call it dt. It's not d into t. Instead of calling it delta t is any change, big change. Delta t could have been 3 seconds. Delta t could be 1 second. But dt cannot be 3 seconds. dt by definition has to be that 0.00000001. But suppose in the previous question we stopped with 0.01, okay fine, that's dt. What I'm saying is not mathematically precise. But right now I want you to get this as an idea, because sometimes people will complain saying what I'm saying is not right, which is correct. That's why there is a delta t. Okay, dt is when it becomes really small. Nobody will complain. 0.01, if all of us are not in agreement, that means somebody did complain, no? If somebody comes, your teacher comes and says, 0.01, how can you take it as 0.01? It's not small enough. Who is complaining? The teacher is complaining. So take a smaller number. So you ask your teacher, what do you want? 0.000001? Okay, fine, we'll take that. At some point, you are going to all agree that number is dt. It is really tiny. Think of it as 10 to the power of minus 40. I don't think anybody is going to complain if you took 10 power minus 40. Correct? What is this delta x then? It's also really tiny. How tiny? We'll call it dx. Now this is what we did earlier. So we will say instantaneous velocity is dx by dt, where dx is a very small change in x. Why was there a small change in x? Because there was a small change in time. How small did you pick? So small that nobody complained about it. Understood? The same logic works here. Acceleration is dv by dt. So what is the meaning of dv? What is the meaning of dt? dx. What is the meaning of d? It is a difference, but it's an extremely small difference. This is a big difference. This is a slightly smaller difference. But there may be people who may say, no, this is not small enough. This is a small difference. There may be people who say that's not small enough. So these are all called delta t, delta x, delta v. But you want to go really small, we call it dx. So what is the meaning of dx? Extremely small change in x. Extremely small change in t. What will be dA? Extremely small change in acceleration. It comes with that extremely small. The word has to have that extremely small. Am I making sense so far? Okay. Once you have understood this, we can go one more step further and start summarizing the set of things here. I will start by writing A is dv by dt. We just wrote that, right? Extremely small change in velocity. That means you want this, at this point you want the acceleration, make for a small change in velocity. Why is there a small change in velocity? Because I'm allowing for a small change in time. And like we did for xt, I can draw a velocity time graph. And if I told you the velocity time graph went like that, and you want the acceleration at this point, if I picked A and I picked B and I said, oh, let's find the acceleration for this, that will basically be for this time interval, how much was the change in the velocity. This is delta V. This is delta T, like we did earlier. Because this is velocity 1, that will be velocity 4 if this was T1 and this is T equals 4. That will be, this by this will be the slope of this line. What line? Secant. So in VT graph, slope of secant from A to B, what is it? Average acceleration, because this by this is tan theta, which is called slope, but it is the slope of this line. But the slope of that line is average acceleration from A to B, is average acceleration from TA to TB. I hope that is clear. But if I decided to take this point and bring this point here, I'll get this slope. Then I brought it here, I'll get this slope. And as I bring it closer and closer, I will end up getting this slope, which is the slope of the tangent. And what will that be? Instantaneous acceleration. So slope of tangent is instantaneous acceleration at that time. If you took the slope here, this slope you can see is less steep than this place, right? It means this fellow has lesser acceleration than that fellow. At every instant, all you have to look at is the slope. You see the tangent slope, which you can imagine how to draw. The tangent slope is acceleration. So far, does it make sense? Okay. Okay. I'm not going to use too much of this geometry and the graph right now, but you have to keep connecting it back at some stage. I just want you to understand these statements. So in a VT graph, slope of the graph is acceleration. In an XT graph or displacement time graph or position time graph, slope of the graph is velocity. So is slope velocity or acceleration? That depends on what are you asking. If it is an XT graph, it is velocity. If it's a VT graph, it is acceleration. In an XT graph, if you join 2 points and you get the secant, it is the average velocity. In the VT graph, you join 2 points and you get the secant slope, it is average acceleration. This slope of the tangent is for a very small amount of time. Look at what is it? That slope is this. So I will call this third step. It is the same as that. Actually, this should have been 1, that should have been 2, this should have been 3. But acceleration at time t is very small change in time. How much was the change in velocity? Velocity as a function of time, starting from here, this velocity is the change in x when you have a small change in time. So are the principles first clear? Okay.